Hello everyone, I am Nezam Rohbani from Institute for Research in Fundamental Sciences, and I present our work entitled PF-DRAM, a Precharge-Free DRAM structure. DRAM's bandwidth and capacity have improved sharply over time in different generations. However, DRAM power consumption and latency haven't improved much over time, which has made the memory wall thicker than before in each generation. DRAMs dissipate about 25% to 57% of entire system power consumption, and a large portion of this power is dissipated by memory arrays during precharge and activation and refresh operations. Furthermore, as you can see in this figure, DRAM cycle time has only improved from 55 nanoseconds to 47 nanoseconds from the first generation of DDR to DDR5. Many of previous work are proposed different techniques to reduce these two main issues with DRAMs, the power consumption and latency, but all of them are based on the conventional memory cell access procedure, which is unchanged from about 4 decades in DRAMs. This work proposes novel memory access technique which reduced DRAM cycle time hugely by about 33%, and reduce DRAM power consumption by up to 54% depending on the executing workload. Okay, at first we take a look to memory access procedure in conventional DRAMs, then we investigate extra power hungry voltage swings in DRAM memory arrays, followed by the proposed DRAM structure called PF-DRAM, which entirely eliminates unnecessary voltage swings in these memories. At the end, we take a look at circuit level up to system level evaluations of the proposed technique. To reach high density and high bandwidth, numerous tiny cells are organized in a hierarchical organization in DRAM arrays. A DRAM module is composed of one or more ranks, and each rank split into many banks, for example, 16 banks in DDR4 or HBM. And all of the banks in a rank receive the same command and execute it in parallel. As you can see in the figure, each bank is made of multiple mats arranged in subarrays, that each mat contains memory cells in a two-dimensional arrangement. When a word line is activated in a mat, all of the memory cells in that word line will be connected to the corresponding bit lines, which is called activation phase. In conventional DRAMs, all bit lines must be precharged to half VDD during precharge phase prior to the activation, while the sense amplifier, as you can see here, is disabled. This is performed using M1, 2, and 3 in this figure to precharge bit lines. By sharing the stored charge in the cell and the bit line parasitic capacitor, a tiny voltage perturbation occurs on the connected bit line. This voltage change is less than 100 millivolts, thus differential sensing of bit lines is mandatory for a robust memory access. For this aim, bit lines are arranged in the pairs, and the voltage of one bit line in each pair is utilized as a reference voltage to determine the other bit line value. By enabling the sense amplifier, the bit line with higher voltage will rise to VDD, and the other bit line will drop to 0 in each pair, and the access cell will be restored with its value again, since it has lost its charge by sharing it with the connected bit line. Okay, here let's take a deeper look at voltage swings on the bit line pairs during different successive access values. You can see all of the possible consecutive values on a bit line pair in this figure: 0 after 0, 1 after 0, 1 after 1, and 0 after 1. As you can see, for example, when the value on the accessed bit line has been 0 in the previous activation, and its current value during the activation is 0 again, we need 2 extra charge of bit lines by half VDD, one here and another one here. The same condition occurs when we have 2 consecutive ones on our bit line. Therefore, regardless of the previous and current value during consecutive activations, this amount of energy will be dissipated in conventional DRAMs. Based on data similarity, up to 90% of values on the bit lines due to consecutive memory access are the same. Both are zeros or both are one. This occurs because of different reasons: data dependency, narrow bit values, high frequently used instructions, and large number of zeros in DRAM. And even if all of the stored values in the DRAM be random numbers, 50% of charge and discharge because of the pre-charge phase are extra. Based on this observation, we proposed a DRAM structure called PF-DRAM, which entirely eliminates extra bitline flips in DRAM imposed by the pre-charge phase. Here you can see the structure of PF-DRAM. The memory cell array is exactly the same as conventional DRAMs, and here we have the sense amplifier exactly the same as conventional DRAMs. But there are two major changes. Here we have two extra tri-state NOT gates which can be controlled using boost L and boost R signals. And here the bitline decoupler and voltage updater are added to the DRAM structure. In this structure, we change the name of bitline pairs in bitlines in each bitline pair to bitline left, BLL, and bitline right. This is because bitlines in a pair do not carry opposite values like conventional DRAMs that you can see here. The memory cell access is based on conventional DRAM principles, but with some simple modifications, which we explain them here. Okay, unlike the conventional DRAMs, which precharge both bit lines in each pair to the half VDD, PF-DRAM preserve the previous value on the bit lines to access memory cell. Thus, based on the previous value on a bit line pair, 4 different scenarios are possible during activation. The voltage on bit lines can be the same as the voltage on the cell in these 2 scenarios, for both VDD or both 0, or the voltage on bit lines can differ from the voltage on the cells that you can see them in these 2 scenarios. For simplicity, we explain the condition that the activated word line connects bit cell to the bit line left, BLL. The same explanation are applicable to the cells that connects to the bit line right. Before activation, both bit lines are connected to each other through M1 like conventional DRAMs to minimize possible noises and keep their voltage balanced. In this condition, BLL and BLR are connected to the internal nodes of the sense amplifier, SAL and SAR, through M4 and M5. By activating the word line and deactivating the M1 at the same time, the cell connects to the BLL. If the cell voltage be the same as the bit lines, BLL voltage and consequently SAL voltage remain unchanged. As you can see in these 2 conditions, by connecting the cell to the bit lines, no change will occur on the bit lines. This is while if the voltage on the cell differs from the voltage on the bit lines, a voltage perturbation equals to Vs occurs on the BLL. Thus, its voltage drops by Vs from VDD or rise by Vs from 0. It's worth mentioning that the amplitude of this signal is twice of conventional DRAMs. After charge sharing, M4 and M5 decouple the sense amplifier from the bit lines and the sense amplifier, and one of the tri-state NOT gates are activated. This extra NOT gate boosts one side of the sense amplifier, which we will have an imbalanced sense amplifier here. And in this case, since the cell connected to BLL is accessed, the tri-state NOT gate that its input is connected to SAL is activated. Thus, in the case which SAL and SAR voltage are the same, because two NOT gates are driving SAR, therefore the voltage on SAL will be dominant and will win the race against the single NOT gate that tries to drive SAL voltage. Therefore, if we have VDD here, the VDD on here on SAR will drop to 0. The same scenario will happen here. If we have 0 and 0 here, since two NOT gates are trying to pull down this value, they will win the race against the single NOT gate here. In the other case, if BLL voltage be VDD minus 0 and BLR voltage be VDD, or BLL voltage is VS and BLR voltage is 0, as you can see here, since SAR voltage is perfect VDD or perfect 0, and the voltage of SAL is degraded from VDD or 0, one single NOT gate here in the sense amplifier win the race against two NOT gates, and the voltage on SAR controls the sense amplifier. If we have VDD here, this NOT gate will win the race against these two NOT gates and drop the voltage from VDD minus VS to 0 in this case, and boost the voltage from VS to VDD in this case. You can see in all of the four conditions, the SAL voltage will correctly determine the stored value in the cell. After the sense amplifier stabilization, the pair of M4 and M3 in this case, in parallel with M1, are activated to update the voltage on the bit lines and recover the stored value in the memory cell. But in many cases, activating these transistors does not lead to a voltage swing on the bit lines, thanks to the high probability of reading 0 after 0 or reading 1 after 1 on the bit lines. Thus, only if two consecutive accessed values on a bit line differs, the bit line's voltage need to swing. For closing a row, only disabling the sense amplifier and extra tri-state NOT gate is enough, and the mat is ready for the next activation without need for a pre-charge phase, and the bit line's voltage in each pair are ready for the next activation. It's worth mentioning that all of the signals are shared between all of the mats in a subarray. Okay. PF-DRAM only dissipates energy on updating bit lines when the previous value on the bit line has value 0 and the accessed cell contains 1. In this case, both of bit lines in each pair are needed to be charged from 0 to VDD, which consume access energy shown in this equation. In the other conditions, the DRAM do not dissipate energy on the bit lines. This is why the conventional DRAMs will dissipate this amount of energy in any access to the cell, regardless of the stored value in the cells. And by eliminating the pre-charge phase in cell access in PF-DRAM, the cycle time of DRAM is reduced by about 33%. Okay, let's take a look at some experimental results here. We evaluated PF-DRAM on single 2, 4, and 8 core x86 system with 8 GB of DDR4 main memory. We compared PF-DRAM with conventional DRAMs in two different systems, and the pre-charge time is reduced to 1 clock from 17 clock, which is more than required time for disabling the sense amplifier and tri-state NOT gate. Two benchmark suites of SPEC and Parsec are used to evaluate PF-DRAM, comparing conventional DRAMs, and at circuit level, we utilized HSPICE with 16 nanometer multi-gate PTM model. Here you can see the voltage change of PF-DRAM internal nodes during VLL access. Here you can see the case that VLL and VLR and consequently SAL and SAR carry the same value, both VDD or both 0. In this case, as explained before, the two NOT gates will win the race against single NOT gate, and the SAL voltage remains unchanged. Only a small glitch occurs here and here, and but SAR voltage will flip in this condition. But if due to charge sharing, the SAL voltage slightly increased from 0, and while SAR is 0, or SAL voltage slightly decreased from VDD while SAR voltage is VDD, the winner of the race will be SAR, and SAL voltage will flip. That you can see it happens correctly in this figure. And after stabilization of the sense amplifier by activating M3 and M4, the bit lines voltage and consequently the cell voltage are updated if required. As mentioned before, in many cases, their voltage is not required to be updated. Here you can see row hit rate and bit flip probability during execution of SPEC and Parsec. Bit flip probability is about 10% in average in single core execution of SPEC workloads, but it increases to about 16% by increasing the number of workloads executing in parallel. This is because of the reduction in data similarity during DRAM access. However, row hit rate drops drastically by increasing the number of parallel executing workloads. This is because of the reduction in the locality of references to the DRAM due to reducing row hit rate, PF-DRAM becomes more effective in power and latency reduction comparing with the conventional DRAMs. And the same trend can be seen more or less in Parsec as well. This figure shows average memory access latency of conventional DRAM and PF-DRAM beside relative IPC improvement in PF-DRAM. In general, the workloads with lower row hit rate benefits more from PF-DRAM. Thus, PF-DRAM IPC improvement is higher for multi-core execution of workloads. And here we show the breakdown of DDR4 power consumption based on Micron DDR4 power model. We modified Gen 5 power model to calculate PF-DRAM energy consumption during each memory access. The I/O termination power consumption plus the peripherals power consumption is the same for conventional DRAMs and PF-DRAM, while the dissipated energy for refreshing and activating the bit lines is reduced by PF-DRAM. The overall power consumption of PF-DRAM over conventional DRAMs depends on the number of writes, row hit rate, bit lines flip probability, and background power dissipation of DRAM. However, in general, the power consumption reduction of PF-DRAM over conventional DRAMs improves by increasing the number of parallel workloads executing. But we can see we have power consumption reduction in all of the workloads, as you can see in this figure. Okay, since PF-DRAM sense amplifier and other added circuits is proposed based on the conventional sense amplifiers, no pitch matching issue occurs for embedding PF-DRAM components inside the mats between the bit lines. Therefore, the overall area overhead of PF-DRAM is less than 8.8%. And based on our evaluation, PF-DRAM is even more robust against process variation comparing to conventional DRAMs, but it is slightly more sensitive to the internal signal interferences between bit lines because the voltage swing on bit lines is larger than conventional DRAMs. But this can be well handled by controlling bit lines charge and discharge speed. Okay, charge and discharge of bit lines on conventional DRAMs to half fidelity during pre-charge phase is a time and energy consuming process. This work proposes DRAM structure called PFD-RAM with slightly modifications in the conventional DRAM sense amplifiers that entirely eliminates the pre-charge phase, which improves DRAM latency and energy consumption. Data similarity improves the efficiency of PF-DRAM, and PF-DRAM works great in parallel execution of multiple workloads. Okay, here you can see the references used in our presentation, and thank you for your attention.